Hi, I'm Dick Seitz. Welcome to the Software Screw-Up series. It's based on the book Understanding Software Dynamics. And in that book, there's a index entry for screw-ups, and there's about 45 of them. This is the first one, about 200 microsecond delay. It goes like this. Here's a network transmission from user code on a client machine to user code on a server machine. The user code on the client machine does a syswrite system call, which goes through the TCP/IP code, which queues up packets to go out into a hardware or ring buffer that the hardware accesses, the network interface chip or card, transmits. The NIC on the other end puts the incoming packets into a ring buffer and also sends an interrupt to the operating system on the server machine saying, wake up and get these packets, which go through the TCP/IP code, which supply data to a read that this user program had issued earlier saying, send me a message. So we have client software, hardware in between, server software. The mystery we're looking at is I noticed in some traces I was taking that from this user request to receiving it over here took about 200 microseconds too long. The question is, where did the time go? Did it go in the write system call, in the TCP code, in the queuing, in the NIC, in the hardware switches in between here, ring buffer, this kernel code, or did the user code not actually have a read outstanding for a while? And so even though everything went quickly to here, there was no read. Until we figure out whether the problem is over on the client software or the server software or the user code on the server or in the hardware, we can't fix it. And so the question is, where's the delay? So you can think of sending packets as this user over here is sending a bunch of juggling pins to the kernel. The kernel takes perhaps one message and turns it into a bunch more pins. Those get queued up. They go to the NIC. They get sent over the network. They receive this NIC. It does an interrupt saying, wake up. This kernel receives a bunch of packets, possibly puts them in order, and then passes them on to this user. This is the process that takes 200 microseconds too long. So at this NIC, if there are lots of different senders scattered all around a machine room, it can get a whole mess of packets all at once. And if it sends an interrupt per packet to the operating system gets overloaded just handling the interrupts and not making much progress processing each packet as it goes. So the solution implemented in all NICs is called interrupt coalescing. And the idea here is at a receiving NIC, hold off sending the interrupt, but keep putting packets into the ring buffer until end packets have arrived or so many milliseconds have passed, and then send an interrupt. So if the kernel over here takes 10 microseconds to handle an interrupt, you don't want to send one every 2 microseconds. You might not even want to send one every 10 microseconds, but maybe every 20 or 30 microseconds to give this enough time to actually do some real work. So what are N and XXX for the milliseconds? It took a long time hunting around on the web to find out what are the default coalescing configurations in Linux. And it turns out the default Ethernet coalesce configuration found through sudo eth2 -CENP4S0, an obvious incantation, has buried in it to hold off for 200 microseconds or for incoming packets. So this receiving NIC, even though we sent a perfectly happy 4 kilobyte message, sits on it for 200 microseconds because the 4 kilobyte message fits in only 3 packets. And nothing else is, if there aren't any other senders, nothing else arrives. And so this guy just waits. Okay, that's the default configuration from like the 1980s, and it hasn't changed. Once we discover that this is where the delay is, the fix is easy. We simply have to change the NIC parameters to something more modern, like waiting 20 microseconds instead of 200. That's the simple solution to this particular software screw-up. Thank you for listening. This is part of the Understanding Software Dynamics Software Screw-Up series. Come back for more. Thank you.